All right. So you see, Dan, it's a little bit earlier than your scheduled time, but I think we could go because also they're probably switching between the other talks is gonna have some delays, and if you know, if not, we can maybe have time for one question or something like that for other talks. So anyway,
Perfect.
all right. So let me introduce now our next speaker. That is Professor Danny Terno of Macquarie University. Now, it's very appropriate to have Danny right after. If you remember from Rob's talk, Danny is one of the founding people of the field, as in the zeroth generation, if we might say, where the thing came out. So it's an honor and a pleasure to introduce my friend Danny, who's gonna talk about the black hole disinformation problem, version 2. So Danny, the floor is yours whenever you want.
Thank you, Edu. Again, thank you for inviting me. It's a pleasure to be here and see glimpses of familiar faces among the black squares and read the familiar names, hopefully next year in real life. And if we started from history, let me also make a couple of historic comments. And the first is that my interest in what became relativistic quantum information actually, now let me see if I can move the slides. Yes, actually started from the black hole information loss paradox. At some point, when I was early in my PhD, a book of Frolov and Novikov on black hole arrived to the Technion library, and I was curious. My knowledge of GR wasn't that great. I mean, even lower than now. And when I was looking through its table of contents, I bumped into the information loss paradox. So now I'll just show a cartoonish version of it, even if I suspect that most of the people here are familiar with. So what's going on? Yeah. So we know that the total evolution is unitary. That means entropy of the entire system is constant. Now we'll try to create a black hole by throwing in structured matter. That means something with low entropy. We eventually get a black hole. There is a Hawking radiation, so the black hole evaporates, and the states inside and outside of the event horizon get entangled. At least in many of the explanations of the Hawking radiation, this is what happens. The radiation, meaning the stuff outside, is nearly thermal, and that means high entropy. Eventually, the black hole is gone, and only high entropy radiation, high entropy stuff remains. That means entropy have had increased, even if it should have been remaining constant. Therefore, we have a paradox. Now, it's quite possible that it was Asher Perez who sent me to look at this book and, a scouting expedition, scheme and report. In any case, after all years in quantum information, and here you see, now let me see if you can see. No. And here you can see 6 founding fathers of teleportation. He was rather keen to return to his old love of relativity. Of course, to get progress and not just to shout slogans, we had to work systematically. And for me, it meant, first of all, going back to special relativity and relativistic transformation laws. And at the same time, Asher started to work on causality and POVMs. And indeed, our work, summary of all the prehistory in Rob's terminology, was summarized in this RMP paper. Now, today, I'll start, or better say, continue with another self-promotion, a systematic overview of the near-horizon physics from the perspective that is very much in line with the topic of this conference and with my talk's title, was recently published. It's a work by Rob Mann, myself, and Sebastian Merck. And I'll discuss some basic principles and, if time permitting, dangle some moderately tantalizing results, starting from what actually is needed to formulate the information loss paradox, and essentially turning the question of black hole existence into a mathematical problem, hopefully reasonably well defined, and then going on extracting properties out of it. So we'll start with making of the paradox. It will help us to formulate precisely what is meant by, well, what do we mean by black hole? It's not that obvious. And then we formulate it as a well-defined question. Once we have a well-defined question, we might have well-defined answers, and I'll say a few words about admissible solutions and discuss some of their properties. There are quite a few of interesting implications, and some of them you'll see tomorrow. Well, it's tomorrow Waterloo time in talks of Pravin Dahal and Sebastian Merck. So let us begin. Making of the paradox, and I have to admit that even I refused to say so for most of my scientific life, a lot of stuff, a lot of things that I'm doing are actually quantum foundations in disguise, and that means a view on the information loss paradox is also from a perspective of a quantum fundamentalist. And here, if we look at ingredients of any paradox in quantum mechanics, we'll see that essentially it's a combination of two sets of ideas. We have classical ideas, classical assumptions, we invoke some classical results or our cherished classical intuitions. We have also quantum features and quantum results. We try to marry them and obtain probability distributions that obviously should be adequate. That means match what is actually observed in the experiment and also satisfy all the constraints of 1 and 2. Examples are, of course, include the well-known Einstein-Podolsky-Rosen paradox, Cauchy-Specker theorem, wave-particle duality, black hole information loss, or firewall paradox. They also come and fit the same pattern. In those cases, classical concept is a classical event horizon, and quantum effects are, well, Hawking quanta that affect the horizon and make the entire story happen. So two essential ingredients are the event horizon and the pre-Hawking radiation. And I'm stressing the importance of the event horizon and not just any other horizon. And there is a bewildering variety of horizons in black hole physics, simply because by its very definition, tracing out degrees of freedom that are outside the event horizon have sort of an absolute meaning and not just admission of temporary technical difficulties. This is what, in principle, allegedly separates black hole information loss from, for example, loss of information in Encyclopedia Britannica if we burn the book and wave the smoke. So let's look at the event horizon. Again, I'm briefly reminding you of some essential features. If we look at classical collapse, for example, Oppenheimer-Snyder dust collapse or anything like that, we can observe it from perspective, at least we can analyze it from the perspective of two observers. Lazy Bob, who stays far away, and this is essentially us, distant observers, and comoving Alice. Then, as everybody knows, from the point of view of Alice, collapse takes finite amount of time, finite amount of her proper time. From the point of view of Bob, Alice just freezes just outside the Schwarzschild radius, which is in Planck units is just twice mass of this object. Again, in modern lingo, quantum black hole, a black hole is what is behind the event horizon, essentially the stuff that doesn't reach distant observers, doesn't reach the null infinity. And singularity, which in the case of, say, Schwarzschild solutions and Kerr solution is manifested as a domain of infinite curvature, is hidden behind the event horizon. So that's essentially a classic picture of collapse and black hole formation. While in practical terms, black holes, collapsing objects, become dark in a very brief amount of time, event horizon in classical physics is an asymptotic concept. From the point of view of a distant observer, collapse is completed in infinite time. Black hole dynamics was developed in the late 60s and early 70s and has a number of remarkable laws. Zero's laws, a quantity which we'll define a bit later. Surface gravity is constant on the horizon. There is a first law which relates horizon area and mass, and you can see changes in mass, changes in the area, changes in the angular momentum for rotating black holes. We also have the second law of black hole dynamics. Black hole area is non-decreasing in any process, including the black hole merger. Now, as a small print, those results are true if the weakest of the energy conditions that I'm going to present in a second holds true. In this case, we also know that boundary of the domain that currently nothing, even light, can escape for it, this boundary is given by the apparent horizon, is contained inside of the event horizon. So as a background briefing, a natural idea that energy density is positive can be generalized and expressed in relativistic situations in several, at least I think 4 different, not fully equivalent ways. Indeed, there is a chain of implications, and the weakest of all the energy conditions is the null energy condition, which says that contraction of the energy momentum tensor and null vectors in general relativity, it also translates into useful relation with Ricci curvature. Good physical reasons to assume that this is so, but in many important theorems, some sort of energy condition, at least null energy condition, is necessary for validity of the black hole dynamical. And surface gravity, here I will just mention that in case of stationary black holes, it can be described as a force per unit mass just outside the horizon. In dynamical settings, there are generalizations, and some of them are about. Story is sort of boring, and well, black holes are really just frozen stars, or at least they were so until Hawking radiation was obtained. Then it was realized that actually black holes radiate almost thermally. Temperature is proportional to the surface gravity, and then conjecture of Bekenstein that entropy is 1/4 of the horizon area in Planck units gets a sound thermodynamic basis. A lot of interesting development happened, in particular Page's evaporation law. Page's evaporation law tells us that rate of mass loss is inversely proportional to the mass squared, giving a simple form of the mass dependence on the time of a distant observer. A lot of worries about thermodynamics were resolved with the generalized second law of thermodynamics, where again changes in entropy of matter and changes in black hole entropy were taken into account. Things looked nice and beautiful. They could have happened because Hawking radiation violates the null energy condition. What was immediately realized by Hawking himself, maybe 2 years down the road, is that, well, we have a problem. Quoting Robert Walt's Living Reviews of Relativity article, we indeed have a situation where a black hole evaporates via the Hawking process if the correlations, so now we would probably more worry about entanglement between the inside and the outside, are not restored during the evaporation process. Then by the time the black hole has evaporated, initial pure state evolved into mixed state, information will have been lost. There are some subtleties, both stringy and quantum gravitational ones, but that's essentially the idea. And the process descriptor was done by Hawking in terms of the superscattering operator, which surprisingly, 1976, the same year that Lindblad theorem appeared, just potentially a form of completely positive dynamics. Since then, there was, in essence, struggle with the paradox. People try to accept it, to exercise it. It might be a law of nature, or there are some different ways why it's a paradox or why it's not a paradox. There is a concise review by Rob, even more concise review essay by Vikar Hossain, Valentina Bachetti, and myself. Sticking to the basic facts. We know that GR is deterministic, quantum mechanics is unitary, quantum field theory is unitary. One way of saying it, we can say classical mechanics of black holes coupled to matter, Hamiltonians exist. That's proven starting from works of Bill Andrew. Quantization is believed to introduce unitary evolution, so we have a problem. ADS-CFT correspondent hints in the same direction. A way that me and I think Rob like to look at it is that we can consider it approximately as gravity and matter degrees of freedom becoming entangled, and then increase in entropy should be interpreted as some sort of entanglement entropy. However, we don't really know what is the state. So the most radical viewpoint, which I love, but I'm not sure whether it's really correct, is that Barre is really realized in nature. Conceptually, it's obviously correct. If there is no event horizon, there is no paradox. This is popularized in the paper of Hayward, from whom I picked up the title, Black Hole Disinformation Paradox. This point of view attributes existence of the paradox to improper identification of black hole by the event horizon. And here you have assorted quotes from Stephen Hawking that show evolution of his views on the subject. Now, more modern perspective range from no, there is no paradox by Don Marolf to probably so what, we have non-unitary evolution, or at least it might happen, by Bill Andrew and Rob Wald. Both are very persuasive and very interesting. Where are we coming into this game? First of all, more careful definition of a black hole. Event horizon is not locally observable. Mortal observers don't know about it. Even God-playing people in numerical relativity look for apparent horizons. Indeed, apparent horizon, while formulation-dependent and potential observer-dependent concept, is also useful for our subjective point of view, the one that I try to attribute to a distant observer. If we follow the light in normal life in flat space-time or in moderately curved space-time, we can have clear distinction between ingoing and outgoing radial geodesics. However, if we have a very massive compact object inside, both types of future-directed radial geodesics will be bending backwards. boundary, oh sorry, the region where it happens is a trapped region. It's a boundary marginally trapped surface. From here, we get to, again, several steps in classification of various horizons, which for purposes of this discussion, I just lump as apparent horizon, both a dynamical three-dimensional entity and the intersection of this entity with a particular time slice. Well, the problem of black holes that sometimes confuses people when we discuss this fundamental question, do black holes exist, is that there is no uniform view what is actually a black hole, and article by Eric Curiel in Nature Astronomy neatly summarizes some half a dozen of views regarding the definitions. Here, I can only defer to Confucius and say that names are important. So,
Danny, you have 4 minutes. Sorry, I didn't tell you earlier.
Yeah. So for us, we take two classes of black holes. Solutions of Schwarzschild, like Schwarzschild solutions of Einstein equations, are mathematical black holes. But trapped regions are physical black holes. Without assuming much more, we try to explore what happens from existence of a physical black hole. We work in the framework of semi-classical gravity, so we use classical concepts. We admit that metric is modified by quantum effects, perhaps additional terms. We stick into the right-hand side expectation value of the energy momentum tensor, but do not assume global structure, singularity, types of fields involved, even the quantum state itself. And basically try to figure out what happens if we extract information from existence of particular solutions. Now, two additional assumptions. One is that this light trapping region forms at finite time of a distant observer. That's necessary if we talk about transient objects like regular black holes. It's necessary if we have any chance of even discussing information loss paradox, not solving it, but just formulating. The second assumption, curvature scalars, contractions of Riemann tensor, are finite on the boundary of the trapped region. That's just cosmic censorship light. And again, that's an assumption that probably everybody loves. As Rob quoted unnamed physicist in one of his emails to me, that those assumptions look so innocent. Their consequences are far from being innocent. Mostly we worked out conclusions of those assumptions in spherical symmetry, but also played with curve idea metrics. So returning to spherical symmetry, we use Schwarzschild coordinates because they are ill-behaved at horizon. And from this bad behavior and divergences, we'll look how to construct finite objects and how to extract information about them. We use invariant mass. We use the Schwarzschild radius as a condition that this invariant mass, as a condition that the function f goes to 0. So radius equals, well, Schwarzschild radius. That's the largest root. There might be additional ones. We look at particular type of curvature scalars. We use particular form of components of energy momentum tensor. They allow us both to write the expressions that curvature scalars are finite in a very convenient form, and also rewrite the Einstein equations in a very convenient form. One conclusion is that essentially only two types of scaling behavior of those effective energy momentum components are possible. By using it in expanding the mass function, we get two types of solutions, as I said. Both look very different from Schwarzschild. If we use useful and coordinate systems, they look slightly more familiar. Essentially, what we get we get two families: white hole solutions, which correspond to expansion of the Schwarzschild radius, and black hole solutions that correspond to contraction. Parameters can be related via the evaporation rate, and we can classify a variety of popular solutions. All of them fit into this scheme. Energy momentum tensor behaves as people suspected in calculations of it on the background of Schwarzschild black hole. Violation of the null energy condition is a mandatory condition for existence of black hole. Without it, there is no formation of black hole in finite time. One conclusion is that out of 4 popular Videa type metrics, only 2 are possible. Physical black holes have a lot of strange properties. They're beautiful. We have finite instead of infinite infall time. Collapse takes finite time. Outer apparent horizon, unlike what is widely believed, is always time-like. We might have weak firewalls without postulating anything, just track energy density for non-geodesic observers when they try to escape a black hole. That's possible. Inner apparent horizon is time-like or null. As a consequence, some popular models of regular black holes do not work. Usual proofs of instability do not apply. And we have a very nice formation scenario that involves both types of solutions and produces, I think, pretty consistent scheme or black hole scheme. So that's probably a good time to ask the question. The main question is, will be there a smoking gun? Whether having apparent horizon formed in finite time can be translated into difference in, say, quasi-normal modes and be observed. So those are tentative conclusions. And most juicy bits are left to the talks of Pravin and Sebastian. And here is the gang. One picture taken in Waterloo, another one in Sydney. Thank you.
Thank you, Danny. Thank you very much. All right, we have time for one question. If you have a question, please use the raise hand feature so we can see you. All right, I don't see any questions. Okay, well, if there aren't any questions, I may ask one for myself.
Sure.
So can you go back to the smoking gun, maybe?
Okay, let me try to get that. Yeah, I can. Yes, yeah.
All right, so can you talk more about that one, because it was pretty fast and I want to hear more.
Oh yes, unfortunately, yeah, it's in 20 seconds. So
right.
Basically, what people who carefully study black hole know, we know that there are ultra compact objects. They have light rings, probably, and they behave more or less like predicted if it's, let's say, Kerr black hole. However, our resolution is just not good enough to really show that those are black holes, it means objects with horizons, and not ultra compact objects, exotic compact objects that mimic their properties, but are just slightly bigger. In fact, quite a lot of work goes into investigation of the differences between, say, Schwarzschild and its exotic mimic entity. What it turns out that there is a difference, and this is a difference in the high harmonics of quasi-normal modes, which might be observable experimentally, not with the next generation of LIGO, but say with the next generation of LIGO. What our work actually shows is that, that between mathematical black holes, Kerr, Schwarzschild, and exotic compact objects, there are physical black holes, objects for which horizon is not an asymptotic concept, but something that happened in finite time, according to the clock of a distant observer. Now, we proved already that there are many properties of those objects that are very different from classical black holes. They also different from exotic compact objects. The task that we're actually looking at now is to see if those conceptual differences can be translated into observational differences. Basically, in this case, the situation will be that it's not a game where we have two players. Either those are exotic compact objects or those are black holes. But it's a game with three players: exotic compact objects, mathematical black holes, maybe as asymptotic entities, and physical black holes, entities where horizon was formed in finite time according to distant observer. And one of the results, which I don't know how to interpret, is that one of the arguments against exotic compact objects that, well, they're exotic, they're weird, they require a violation of null energy condition, negative energy density, and all kinds of bad properties. But physical black holes require the same bad properties. So life just becomes very interesting, and we would very much like to figure out what happens, if you perturb those objects, if you sort of pinch them and they ring, and if they ring the same way, if they ring differently, and how, and then it will be possible to see if there is a difference. So that becomes, from a philosophical question, becomes a very practical question.
Thank you, Danny. That was great. I was thinking that also, I mean, it's going to be very late in Australia, but Luis Garay is going to talk about this stuff in his invited talk too. Well, this stuff, they do use kind of like send a wave towards a compact object, and depending on how it spits anything back or how scatters the radiation, right?
Yes, that's another way of basically trying to detect what do we have: exotic compact object, a black hole, and then what type of a black hole.
So I don't want to make it much longer, because again, the schedule is tight. But yes, that talk will be recorded too, Aaron, so you will be able to.
So basically, the idea is, you want to have a paradox, you have to have physics before you can have a paradox.
Right.
And what happens to it, you'll see tomorrow, I guess. Thank you.
All right. Thank you very much. Let's thank Danny again, please.